Okay, picking up where we left off, we're on page 94, getting ready to talk about the advantages and disadvantages of this bus type of technology. So, particularly the carrier sense multiple access collision detection. So first of all, it's very simple and cheap to produce. There's nothing in here that's very complicated. So if you're a hardware manufacturer and you're trying to build an Ethernet card, Ethernet cards are cheap. Most of them are implemented now on a single chip inside of a motherboard or on a phone or something. The idea is that mechanically and electrically, it's not that tough. So there's no special hardware, special software. And how much smarts does it take to plug in? You buy a new computer and you want to plug it into your hub or your switch. You got an Ethernet cable and you plug it one end into the computer, you plug the other end into the port where the switch is, and that's it, right? You don't have to do anything else. You don't have to go in and configure anything. Nothing. It just magically shows up on the network and everyone talks. So it's easy to build and dang easy to maintain and implement because there's hardly anything to do. You just jack the thing in and we're up and running. Conversely, if I want to pull a cable out, the whole system doesn't go, ah! You just said, well, Bob's machine must be turned off. Okay, whatever, let's continue working. So there's nothing fancy about that. Okay, now there are some alternatives to this type of technique, and just the text kind of brushes over them, so let's just talk about it a minute. You could, instead of having all data being sent on a bus, you could have it like the message length. You could prioritize it by the message link, or some sort of a priority system, or some sort of a computer ID tag where, my machine's more important than your machine, that kind of stuff. And all this tends to complicate things. Because right now, the Ethernet card that's in your computer, and I'm using card in the that's a good choice of words. Anyway, not necessarily a physical card, but it could be just a chip on a board. Anyway, the idea is that these cards don't have hardly any smarts, and they don't need to know anything about the machine they're plugged into. They don't need to know any hierarchy of machine or who has higher performance or priority. It doesn't have to know anything about that. So once again, it's dang simple. Now the problem is this is not very scalable. Okay, I can't put like 1,000 machines on a single Ethernet network. It just don't work. Most people who've tried this in real life figure that 250 is the absolute upper limit of being able to get acceptable performance. And quite frankly, the number that everyone likes is about 100. So about 100 machines on a single Ethernet segment. And again, that's not what the standard says. I'm talking about real life, where people who have tried this and went, man, that didn't work. Okay. So let's talk about this whole collision detection thing. So if we start talking and I have to stop and then I have to wait a period of time and start talking again, there's an awful lot of physics behind this. And so I'm not going to bore you with the math. I'm just going to run kind of through the math. So what's the propagation speed of an electrical signal in an Ethernet cable? It's probably around 70% of the speed of light. I want to send a packet that's, let's say, 512 bytes long. So doing the math, what is the minimum amount of time it takes for a signal on one end of the cable to get to the other end of the cable, right? So if I have a cable length in the Ethernet world, let's go for the maximum. 2,500 meters is the absolute maximum length between any 2 points in an Ethernet kind of a scenario. So 2,500 meters, I know what the speed of light is, I know what this packet size is, and you do the math and it comes out that there's this amount of time, 51.2 microseconds, but who cares? It's not a math class. There's a period of time it takes for the signal to go from point A to point B. So everything is designed around that signal delay. And when I send a signal, I have to wait that long before I can expect to see whether or not I have a problem, right? I mean, if it takes 2 seconds for you to figure out that there's something wrong, well, then I can't start transmitting every 1 second, then can I? Right? So this is a very powerful number, whatever that delay number is. Okay, so because of that delay number, these things are not very scalable. I just can't throw in a button. I can't make them any longer. I can't make them all that much faster. I can't throw more on there. Okay, let's continue. So on page 95, they start talking about error detection. So first of all, what kind of errors are we talking about here? Well, most likely we're talking about collisions, because that happens a lot. I mean, particularly if you had like 250 PCs on a segment, yeah, you expect to get one heck of a lot of collisions. In fact, you'd expect that probably around 30 or 40% of your traffic would be collisions. Okay, so that's a lot. All right. So collisions and noise. It's very likely that there's electrical noise, other things going on in the office environment. Maybe you have a generator over in the corner, or one of the weirdest ones that puts out a lot of electrical noise is an uninterrupted power supply. And typically you put those in server rooms, right? Battery backup in case the power goes out. Those things are incredibly noisy. Don't ever run a cable along the back side of, or right above on the wall, one of these guys. Those guys need to be sitting out in the middle of the room and have all cabling all the way around them. Okay, let me get back. So, how do you detect this? Well, you detect this with what's called a cyclic redundancy check. It's a mathematical procedure, and once again, this is not a math class, so I'm not going to bore you with all that. But let's talk a CRC. What's the redundant? What on earth do they mean by redundant? I mean, redundant sounds kind of weird here. Well, redundant in the context of data communications, which is the title of this course, is it carries no information, no data. It's metadata. In other words, this CRC gets tacked onto the end, but it's not has anything to do with the data. It's something extra or redundant. Okay, that's how that came out. Okay, so let's talk about how you, in another environment, let's talk about how you would determine whether or not you had a transmission error. So in the real world, human to human, okay, no fancy computers here, human to human, let's say you're on the phone and somebody has to give a credit card number, and you want to make dang sure that the person that's giving you the credit card number, you've got it right. What would you do? Well, a very likely thing to do is you repeat it back to them. You echo back the numbers. So if I said, 1, 2, 3, 4, 5, 6, they would be at the end. They'd say, okay, let me repeat that. 1, 2, 3, 4, 5, 6, and you go, All right. So that's one technique that you can use for error detection. Is I repeat it back, and you go, yeah, or you go, no, that's not it. That's one technique. The other end is you send redundant data. And so this is a little more complex to come up with an example. But let's say I sent you a note that said, the meeting is going to be on Sunday the 23rd. And you could look at the calendar and go, whoa, Sunday's not the 23rd. Something's wrong. So I gave you two pieces of information that you could kind of corroborate, whatever that word is. Sunday, or some redundant information, the 23rd. And you could look at that and go, wait a minute, I must have missed either Sunday, I must have heard you wrong, or I must have heard the 23rd wrong. So redundant data. And then the third technique is simply, I'm sorry, could you repeat that? You think you don't have it. And so you just say, sorry, huh? What? That's the third technique. Okay, so let's say you want to build this into a computer network, which is, again, what this course is about. So the first technique, the echo technique, that would be kind of bad, wouldn't you think? I mean, every packet I'd have to send back to you so you could check to see if it was okay. Ugh. That'd be extremely inefficient. So I don't want to use the method because the method requires another party. In other words, it takes someone else to say, I'm sorry, did you get that? I want a technique where I can determine on my own whether or not a packet came in and it was a good enough shape. I don't want to have to ask. I want to figure it out on my own. So that's what this is all about. So the original way of thinking was this term called a checksum. And the idea is that I would take like hello, the phrase hello, take every, the ASCII letters and then add them all together. And then when you sent them to me, I would just do the calculations over again. And so you told me that here's the message, hello, and here's the checksum. I got the message, and I do my own calculation. I go, whoa, the checksums are not the same, so there must be something wrong. That's a really cool way of doing it. The only problem is checksums don't work with transposition errors. In other words, HELLO in a checksum comes out the exact same as EHLLO, right? Because changing the order of the H and the E mathematically doesn't change the sum. Okay, so then they decided, well, we'll come up with a more complex way that can do transposition errors. That's how the CRC was born. Now, the CRC is not one algorithm. There's like a half a dozen of them. Some of them are designed to around how big they are, how big the checksum is. CRC 16 is 16 bits, and CRC 32 and 64. And there's lots of different ways you can go in and tweak that. Obviously, because it's a protocol, we both have to agree on what technique we're going to use for our CRC. Because if you're using one algorithm and I'm using another, then we're obviously not going to talk. So, once again, there's some boring math that we're not gonna deal with. We're gonna skip that. So, moving right along. So it can detect an error, right? So what does it do with the error? Well, if the checksum fails for whatever reason, we just discard the frame. That's it. And if you're thinking to yourself, you've got to be kidding. It's no more complicated than that? The answer is no. It is not any more complicated than that. All right. So to make this thing work, we have a frame, and the frame has a header, and the header has, the to and the from and some other little goodly things. And then at the end of the data, we throw this little checksum at the end. So it's a trailer. So basically we're building an envelope. And so inside the envelope is the data, and the outside of the envelope has the to address, the from address, and a code in the corner, which is the mathematical sum of, well, not sum, but the cyclic redundancy check of everything having to deal with what's in there. Okay, kind of makes sense? Good. So, let's look at what this goofy little frame looks like. Here's what it looks like. So, here's my destination address and my source address, my data, whatever that is, and then this is my thing at the end, my frame check sequence where the CRC goes. So this is like the trailer, 4-byte trailer, and then all that. So let's just kind of go through this and talk about what each one of these things are. All right, first one is what's called the preamble. And the preamble is 7 bytes long. Now, if you're looking at that going, 7 bytes, isn't that kind of sort of a lot? Yeah, that's a little weird. And the answer is, yeah. And so it's just a special bit pattern, 7 bytes long, that's sent along the cable, so the machine can look at that and go, wait, this looks like a good Ethernet frame rather than noise. And it was specifically designed to be something that you would not find as random noise. Typically, noise isn't going to be exactly in synchronization with the modulation going on. It's going to be like everything goes to ones or everything goes to zeros. It's not going to be lots and lots of ones and zero noises. Okay. Once again, this is probably a good place to stop for the 15-minute mark. We'll continue this in just a second.